Good morning to everyone. I'm Dr. Sumi MS. The topic of my today's presentation is influence of size, shape and interface in composite applications from Unit 3 Nano Composites. On completion, the students will be able to understand the influence of size, shape and interface in nanocomposite applications and also be able to describe the design guidelines for nanocomposites. Influence of size, shape and interface in composite applications. Particle or filler size effect. So here we shall compare both nanoscale versus microscale particles. Nanoparticles exhibit dramatically higher surface area where the filler size is decreasing from a micrometer range to nanometer range and the surface area gets increases in the range of 10 to the power 6, thereby boosting the interface influence. And the mechanical stiffness and tensile strength also improves significantly in the case of a nano-sized filler rather than a microscale filler, whereas in microscale inclusions they have minimal effect on the stiffness. At higher volume fractions, smaller fillers improve the toughness and the debonding resistance increases and fracture energy is dissipated at the interfaces. Edge cases. Excessive nanoparticle content can lead to agglomeration, defects, and reduced strength. Filler shape and aspect ratio, the geometries. Spherical shape. Here it has moderate toughness, uniform stress distribution. And in the case of a rod like shape, that is example carbon nanotips, these have most effective in the case of reinforcement matrix and enhanced stiffness but with risk of interface stress concentration and debonding. Then platelet shapes, that is for graphene nanosheets, they improve the toughness and flexibility with less stress concentration than the rod-like nano composites. Aspect ratio influence. Higher aspect ratio increases the reinforcement and stiffness and strength scale up, but interfacial peeling risk is increased. And alignment of high aspect ratio fillers maximizes the load transfer along specific directions. Here we shall see the role of interface. Interface is the boundary region between the matrix material as well as the nanofillers, and they are typically zero point 0.5 to 4 nanometer thick and may include functional coatings, sizing agents, or grafted polymer chains that alter the mechanics and adhesion properties. Mechanical role. Stress transfer. Good bonding at interface enables applied loads to transfer to reinforcement critical and it's critical for stiffness and strength enhancements. Stiffness and modulus impact. Higher interface modulus increases composite stiffness, that is doubling the interface modulus can boost the stiffness by about 112 percentage with a filler of about 30 percentage increase, and increasing the interface thickness can also stiffen the composites even though it has less sensitivity. Toughness and debonding. Interfaces can absorb energy during debonding, and here we have cohesive zone that shows how the interface strength and the friction affect the failure behavior. Controlled interface properties prevent brittle failure, that is breakage due to brittle, and also improve the toughness in the material. Interface morphology. Smooth, defect free interfaces, example metal type of laminates, maintain high strength and also they are rough. In the case of rough or deteriorated interfaces, it has lower load capacity. Interfacial optimization strategies, surface treatments, sizing fibers, grafting polymers, Functionalization and coupling agents. Chemical bonds or hydrogen bonding can improve the load transfer and wear resistance. Controlled filler dispersion. This ensures uniform interface and obtain efficient stress pathways. Tailored interface thickness. This can optimize the stiffness versus flexibility trade off. Design guidelines for composites. So the design guidelines includes the parameters size, shape as well as interface. So with respect to size, the target properties of the composites are high stiffness and strength, and the design strategy includes the use of nanoscale fillers avoiding agglomeration. For the parameter shape, the target properties are directional load bearing and it has a high aspect ratio assigned structures. And for isotropic properties, here the spherical or short fibers are dispersed evenly. And interface, with respect to the interface parameters, the target properties are effective stress transfer as well as toughness. And the design strategy includes strong chemical bonding, proper sizing, and also introducing energy absorbing debonding zones. Practical applications examples: Z pinning. Fibers inserted through the thickness improve delamination resistance. That is, it's an interface engineering tactic to arrest the cracks in the material. Nanocomposites mimicry. Tooth enamel inspired alignment of rods yields excellent toughness and lightness via tailored interface structures. Quiz questions on influence of size, shape and interface in composite applications. Explore the influence of size, shape and interface in nanocomposite applications. Describe the design guidelines for nanocomposites. Write down few practical applications of nanocomposites. Thank you.